Well, ladies and gentlemen, the last video kind of snuck up on me there at the end, and it cut me off, and I didn't even realize we were at the 15-minute mark, so I do apologize. But, as I was saying, if you go back and look at the previous slide or look at your notes, there's a 1 and a 2 that you can combine to get 3, and that's antiderivative is 3 theta, and then here are the rest of the antiderivatives. Now we can plug in our numbers, and you get this big, long string, and certainly, by all means, pause the video and see if you can simplify this yourself. I did simplify it. You get 3 times 2 pi in the end, which is 6 pi. And, of course, all of this here goes to 0. And 6 pi is your answer. Now, of course, you see the example 7, finding area with a calculator. We will certainly, on this one, use a calculator to come up with the answer. So we want the area inside the smaller loop of this limacon. Those of you that are fluent in French or know anything about French, there should be a little tail on this C, which of course makes the S sound in French. But I don't have that key on my keyboard, so this is the best that I can do. So we make our sketch and we have this, and our job is to find the area inside this loop right here. Now how do we find in this side the loop right here but not the whole thing? Well, it's very simple. I find the angle measure where we get to the origin, and then I find the angle measure again when it circles back around after going through this inner loop. Again, use your tables, and you come up with 4 pi over 3 and 2 pi over 3. Another way you could do that is you could set this equal to 0 and solve. And when you do that, you bring your 1 over, divide by 2, take the arc cosine, and that's how you can get these answers also. Now again, this would not be a terribly impossible integral to find, but just for the sake of time and using a calculator, we will do the calculator. I can pull the 1/2 out just to make it a little easier. But when you multiply that out, work it all out on your calculator, 0.544. Area between polar curves. Now, the ones up to this point, we've had one curve. So let's say we now have 2 curves, R1 and R2, for thetas, again, between alpha and beta. To find the area between the curves, we do this right here. We'll take 1/2, just like we did before on the previous polar curves, and we square the polar function just like we did before, but you do the bigger one, or the outer one, if you will, minus the inner one. Now this is a lot like the area between curves when we dealt with lines and curves and things, because it was, you remember, the larger function squared minus the lesser function squared. Same thing here. And we're going to find the area between these curves. Find the area that lies between the circle r equals 1 and outside the cardioid r equals 1 minus cosine theta. Let's start by making a sketch on your calculator. Looks like this. So my job is to find the area right here. You got to find these 2 things right here. Now, I'm going to take the integral from negative pi over 2 to pi over 2. How in the world do I get negative pi over 2 to pi over 2? Well, I'll start out, I want to know where these 2 things are equal. Where do they intersect? So I set r equals 1, so I set 1 equal to this. So 1 equals 1 minus cosine theta. The 1's cancel, and essentially cosine theta equals 0. Now, where is cosine theta equal to 0? Cosine is equal to 0 at pi over 2 and 3 pi over 2. But if you look at that, that's not what we want, because if you go pi over 2 to 3 pi over 2, that starts here, and it goes in this direction right here. We want to do negative pi over 2 to pi over 2, so it will start here and actually move on the inside here. And that'll give us the point on the inside. And again, you can use the tables on your calculator to verify that. So we have this. We can simplify it a bit. This is 1 minus 2 cosine theta minus cosine squared. That's 1, so the 1's cancel, and we have this right here. Now feel free to use your calculator if you wish and get 1.215. I will, again, I know I've said this many times, but the tables on these, the tables, the intersect functions, all those capabilities that you have on your calculators will come very, very handy. They'll be very, very useful as you work these problems. Now, ladies and gentlemen, we want to take a moment just to look at some of the graphs. What are some things that you can see when you do polar graphs? Obviously, one thing that you can graph is a circle. We've done several of those, and you see down here the formats for what circles look like. Roses, you see. Now, if I can go back, This graph right here could be a rose, could be a circle. And because technically it looks like a circle, but the format looks like a rose. So if you call it a rose or circle, either one is fine. Alright. Here are our roses. And again, you see their formats and about how many petals you get. The limestone looks like these. And you see the ones with the inner loop, the ones with the point right there. So there's a loop. With a point, it's called a cardioid. Sometimes you don't come to a sharp point. Sometimes you just bend in a little. That's what we call a dimpled limestone. And again, you see with the A's and the B's here, given up here, you see the restrictions and you know how to tell which one is which. And then we even have some that are convex, some that actually jut out just a little bit. This is called a lemniscate curve. These are easily recognizable because they have R squares and they loop around. Now, these are kind of like these are kind of like roses, but the problem is you don't have something up here and you don't have something down here, because that's where you would end up taking square roots of negatives to solve, and it's imaginary, so we don't plot it. And the last is my favorite, is the spiral. Spiral is just R equals theta. R equals a number. I'm sorry, not a number, but just R equals theta. Maybe theta is times a number, 2 theta, 5 theta, 10 theta, or just theta. And we get this nice little spiral shape. Now, normally the spiral will stop about right here. That's 2 pi. But if you wanted to continue on, you just increase the value for your theta, and it'll just keep spinning and spinning and spinning. And that, ladies and gentlemen, sad to say, is probably the last lesson I'm going to teach you. We'll answer lots of questions for the rest of the year, and we'll take lots of practice tests, and everyone hopefully will be ready for their AP exam.